Just before I begin, let me give you the background to this presentation. In a former life, I had a job where I went to pretty much every test lab in the United States, certainly in the Americas, and including Brazil, Argentina, and Canada, and I saw a great many test chambers, all in various states. Many of them showing their years, because once you've spent $2 million on an EMC test setup, you're probably unlikely to get more money for a good many years, and most of the labs I saw were getting on in years, and it was the observations I made during those many visits that prompted this presentation. Here we have a test setup, and it looks very simple, but holds a lot more information than you might at first think. First of all, observe there's a horizontal line going from where the connector, the bulkhead connector of the chamber is, goes along in a straight line through the antenna feed cable to the antenna, and then the two little diagonal lines, the diagonal lines of both the blue and the black set there being the distance not as shown. And then we have a field probe, and note where the field probe is. It's on that horizontal line. Reasons it's there is you can get a far more predictable result if you're fault finding a test chamber setup by monitoring the bore site field strength rather than trying to take some point elsewhere in the calibration plane. In fact, you'll find the bore site is not a point on the calibration plane, but I would strongly recommend, if you are faulting the system, to put it on the bore site. You can calculate what it should be approximately, and it will be very consistent rather than taking the variations that go with field strength across the calibration plane. Now, the first antenna I showed you was omnidirectional. That is, as much of the power goes backwards as goes forwards. And one very good reason for having a straight line feeder going straight back horizontally is that you get the minimum illumination of that cable in terms of pickup. And even with an antenna like this, which has a vastly superior front to back ratio, where there's probably got 1/100th of the power going backwards along where the cable is compared to the forward direction, I would still argue that good engineering is good engineering practice, and whatever the type of antenna you have, that is the ideal setup according to me. And similar, I would argue there's the same engineering principles apply when you're doing emissions. So on the rightmost there, they've got an equipment under test of sorts, and it's emitting noise signals. The antenna's picking them up. Then you have a preamplifier there which boosts the low-level signals, and again a straight line feeder going straight to a point deliberately put where the bulkhead, in my view, should be, which is on a level with the center of the calibration plane. So if I've been to so very many laboratories, I should have a war story or two. Well, I've got a couple of favorite ones I'd like to share with you, where I've actually witnessed events during test laboratory visits. This first one, this was for a low frequency test. It was the low frequency test immediately tells you it's a poor match low frequency antenna. Even with the best test chamber, fully anechoic, perfect chamber, you're going to have a very poor match at lower frequencies because of the nature of the antenna. And because you have a very poor match, you need a high power, low frequency amplifier to drive it, particularly at those high mismatch frequencies. So this is what was happening prior to me ringing the doorbell of the test lab. They opened the door for me, and in I went, and there was an embarrassing whiff of overheating fiberglass substrate. I think anyone who's been in electronics for a while knows that embarrassing smell, and you know something is very wrong. And the friend I had come to visit, he was in charge of a test, and it was from his test equipment that the embarrassing whiff was coming from. And it proved to be an underrated component. Just by chance I was there and I could help them because I'd been doing RF for quite a few years. And many EMC test staff, these are first-class guys, many of them graduates, and they know everything about electronics and know everything about electrical theory, but they haven't been a lot of direct experience with radio frequency theory. And I found that invariably these guys were stuck in what I call fast AC theory. They know all the AC theory principles really well, and they try and apply them to RF, and basically it doesn't work. So I actually came back and I helped them find what the issue was, and then I gave them a talk on making the leap from fast AC theory to RF theory. And here's the culprit, and here's the background as to why there was this embarrassing smell. This was for an automotive test, high power, but it was on-off mark space ratio, equal mark space ratio test. So they'd have the RF on for a short while, then off, then on, then off, and on and off, running kilohertz or whatever. And the person who had ordered this component part and this coupler that you see there on the screen, he had quite rightly rated this at 500 watts CW. Well, how could you do that if there's 1,000 watts going in? Well, it's a 50% duty. So on average, the dissipation will, in fact, he was dead right, be 500 watts CW. CW means continuous wave. There's no on-off switching going on. So there's your component, and it's has 500 watts going through it. On average, everything should be fine. What he didn't take into account was not only would the component have to handle with dissipation in the forward direction, it would also have to handle the separate reflected wave coming back at the component. So you've got two lots of dissipation. And you'll notice that the 800 watts coming back, well, how can that be? Well, these guys were calibrating. So they didn't have the on-off situation going. They had CW as a continuous power going on into the input there. And because they were struggling to achieve the field, you guys who have been doing low frequency immunity testing will recognize that you often struggle to get that field at the lower frequency. They had this amplifier turned right up the best it could, and it was giving out 1,200 watts. Well, because of the very poor match from the antenna, 800 watts was coming back. So now immediately you've got a problem that the guy who designed this didn't take into account that you would calibrate at CW. And you had 1,200 watts CW going in to this poor component. And, as mentioned before, you'd also got 800 watts coming back separately and creating its own dissipation as it passed through the component. And this poor guy was rated at 500 watts CW, hence the embarrassment smell, and it destroyed the component. And here's another favorite war story of mine, and this one's very pertinent to this presentation, which the presentation really is about, as you get older test equipment, by older test equipment I would say 10 years plus, you get issues, and you should be prepared to deal with those issues beforehand. So this was an automotive supplier, and they had their own pretty good test setup, but it had been, they were testing, there was a new test where they had to do 200 volts per meter or 1 meter over the L and S band radar bands. That's 1.2 to 1.4 gig for the L, and 2.7 to 3.1 gigahertz for the S band. And so I went along trying to sell them this piece of equipment, and it was to hook the equipment. It was a high power amplifier, and I was to hook the amplifier up to this. That's a side view of cross section of a bulkhead connector, through connector, which was the amplifier was going to be hooked onto the left-hand side there, and then antenna on the right. And I immediately noticed, I could tell straight away that the chamber was pretty old, it's in better days. And there was something called patina all over the bulkhead. What's patina? Well, if anyone's ever watched the Antiques Roadshow on the television, you know what patina is. If you find a coin in your backyard and it's 1799, it's not going to be very shiny. It'll be covered in various blacks and maybe parts of oxidized or whatever. And the worst thing you could ever do is to buff that up and make it all shiny again. You'll lose 2/3 of its value. Well, that's the sort of patina I'm talking about when I was looking at this bulkhead connector and connecting my amplifier up to it. Now, to achieve the field, this needed 550 watts over the L band there, 1.2 to 1.4 gigahertz. So I duly hooked up the amplifier, switched it on, and we started monitoring how much field we were achieving. And within a very short while, I would say within a minute, there was this terrible, terrible smell coming out from the back of the amplifier. And it stank to high heaven. I thought, oh boy, this is embarrassing. They're probably not going to want to buy one of these amplifiers. But I thought it was very good because one of the production tests of this amplifier was to run at full power into a short circuit and made sure it survived. So I was at a loss to explain why this amplifier should be failing and giving off these terrible smells. And but it turned out to be it wasn't the amplifier at all. When we undid the cable from the left-hand side there, the whole thing collapsed inside of the connector there. What had happened was there was so much dirt and grime inside that connector that when this new high power, they hadn't done this before, this was the first time they'd used it at pretty high power, certainly in excess of 500 watts. There was local heating where the grime was, and that local heating heated up the insulator inside the connector there, and as the insulator got hot, it lost its properties and began to get very lossy, and it got hotter still, and they ended up with thermal runaway, and it pretty much fried inside of that. It was pretty much just like black soot or ash inside there when we had a look inside, and basically it failed pretty much through old age. Because I think we all know that with the test setups, you're always forever putting the test together and tearing it down, putting it together and tearing it down, and eventually you're going to that connector is going to wear, it's going to degrade. So it's a truth that all connectors do have a finite operating lifetime. And reading this to you, and any connector, and this is any connector of whatever standard, is usually specified by the number of mating cycles. And a typical one in our industry, in the EMC industry, would have a number of mating cycles of, say, 500. So if you've got a 10 or maybe even a 15-year-old chamber, there's a good chance you're close to or have exceeded those 500 mating cycles. So no matter how well designed, connections and disconnections result in wear and tear. That's that patina. But look at this, guys. They were all very horrified. I mean, they thought, oh boy, chambers are a fortune. We're going to have to get the original supplier or someone who's willing to do the maintenance. But the replacement was very, very simple. Just take a second or two to look at that picture. Have you ever seen anything simpler than that arrangement there? You take the old connector out, which was completely ruined. You put that one in, direct replacement, and you fasten up to the required torque, and you're ready to go again with a brand new connector complete with its 500 mating cycles. And I think what I'm arguing here is then, especially if you do have an older chamber and long since out of warranty, you shouldn't really treat it as a holy relic that only geniuses should attempt to repair, particularly with a bulkhead. In fact, but I would argue that you take your bulkhead and you put in more than one connector, and you dedicate one of those connectors to receive only for emissions testing, and you dedicate another one to high power testing, and run them separately. It's very, very simple mechanics. Now, in my time, there still is something called connector savers. What's a connector savers? If you've got a very, very expensive instrument and you're doing a series of RF tests, scattering parameters or something along those lines, and it has to be extremely accurate, then rather than you connecting directly onto the connectors on the front panel of that very, very expensive piece of equipment, test instrument, they provide you with, at a good cost, special gold-plated savers. The kind of, you put them on your end types, and you actually get your finger and thumb in around the back, and you fasten them up in that fashion. It goes on input and it goes on the output. And basically the idea is that they'll take the abuse. The idea is that they preserve the quality and integrity of the connector, because it swallows all the abuse, and as soon as they get, say, a year old, you replace them. Expensive thing to do, but you replace them, and it saves you having to send the test instrument all the way back for them to replace the front panel real connectors. But for our purposes, for chamber tests, for EMC and the power levels we're working at, we could, and I would recommend for someone who's got an older chamber, who's not too concerned about maintaining the warranty, etc., to use connector savers. Look, if you know all full well that the connectors on your bulkhead there are past their useful life and need to replace them, I would recommend you replace them, and also you use these readily available adapters as connector savers. So I would have, if it was my test lab and the warranty was long since gone, on that metal plate we call the bulkhead, I would put an N-type through, and then I would put on, can you see the N to SMA connector there, adapter? I would put that on both sides of that, and I would mark them with a bead of paint to make sure they haven't been undone, and to discourage others from doing it. They'll see that and they'll say, ooh, maybe I shouldn't take that off. But there's some very low-cost solution to the problem of wear and tear on an older EMC chamber. Now, there are alternative bulkhead connectors with powers going up and up, power and frequency going up. It would seem every 5 years there seems to be an increase in power and increase in frequency. But there are other types. Type SC, not everyone's familiar with these, but that's a high power type N. The thing is with about a high power type N, if you imagine the two parts joining together, there's actually only air between the inner and outer conductor when the connectors are joined together. Type SC, and they're fully interchangeable. You can use a Type SC with a Type N. Type SC, rather than having air there, they have a cylinder of insulator, of special insulator, allowing you to work at higher voltages and higher powers. So on this bulkhead, if I was a lab manager, I'd have Type N's, then I'd have Type N with the adapters for SMA for emissions only, and then I would have Type SC for higher powers. And why not? It's not a holy relic. And this is a favorite of mine too. I used to work in the telecom side of things first, and they invariably, all these base stations you see with the antennas going up the poles there, they use something called a 7/16 connector. That's not 7/16ths of an inch. It's the ratio of the inner to outer diameters, and it's 7/16 ratio. The ratio is 7/16. Just one word of warning, though, they're only good to 6 gigahertz, but you just have to look at them, see how rugged they are, how strong they are, why they're used invariably in telecoms. But another very good reason for them being used invariably in telecoms is they have fantastic intermodulation performance. But I'd put a label on there, only good to 6 gigahertz, and I'd have one of those too, through one of those too. Oh, just a word here, because I've seen people not do it. Whenever you see an RF connector and it's not in use, put on a 50 ohm termination there, because it's just, why have that floating? It's just good RF engineering practice. Always, always terminate your unused connectors in 50 ohms. Oh yeah, and another reason why you might want to consider, and you would mark the plates, the bulkhead plate accordingly, separate transmit and receive path, separate immunity and emissions paths is, I hear from AH systems that every now and again they get an antenna back with the balun fried just over too much power, and basically the reason is it's designed for low power receive signals, and you're not supposed to use it for immunity, and someone didn't realize and put it on the wrong path, no doubt. So that's another good reason when training your staff to have actually dedicated paths, one for emissions, one for immunity. Now, what I'm going to recommend here is when you've got one of these older systems, imagine your mind's eye, some 10, probably older EMC test setup, and probably needs quite a lot of replacement. A lot of the equipment's at the end of its useful life, is to have ready on hand should any of these parts of the test system fail. You can very quickly get back online because you have data already held on file that you can do. You can make tests and compare with that data to see as a fault finding process. But another reason for doing that anyway is the auditors love data trend analysis. If they love it if you as a test manager are keeping an eye on the performance and looking for degradation of that performance of your test system. So if you have information on file, all filed away in your filing cabinet, and the auditor asks you about such matters, you can pull it out and then you say, well, every 3 months we make this test, and as you can see over the last 3 years there has been no degradation in performance. They love you. It puts you in very good stead during the audit. Now, I would suggest that you make very simple tests, 5 single spot frequencies, and as I said beforehand, make them bore site readings. You've got too much variation over that calibration. Put the field probe dead in line with the antenna and make that. A good few years ago I actually did this, and I was surprised at how accurate it was. That when you work out how much power is going into that antenna, you have to take into account cable losses and so forth, how accurate it was 3 meters away, just how accurate that predicted field strength was. You'd be surprised how accurate that is. So for instance, you should have on file the preamp performance data on file. Same thing, very easy. Both these procedures stress that you first have to calculate that you're getting less than the damage level of an instrument. If you're using an instrument, a spectrum analyzer as your measurement instrument, and it can, the maximum, if the no damage level is plus 10 dBm, you need to make sure you don't exceed that, because the last thing you want to do when you become self-sufficient at fault finding your own test system is to blow up an expensive test instrument. So there you are. You've got a test lab, and you've already got all this existing diagnostic tools. You've got a coupler, and that you can look at forward and reflective power and find out whether an antenna's dead or it's not performing as it should. You've got a signal source, of course, for your test, and you've got a test signal monitor, an analyzer of sorts for the scalar vector or spectrum, and of course you've got your bore site mounted field strength monitor. You've got all these at your fingertips. And should you need more power, and sometimes you do, you've got your preamp, which comes away as you can see there, your preamp. And if you need more power, you do of course have your power amplifier itself. So you're actually pretty well set up in many ways to do some basic simple tests that allow you to get your system online quickly should it fail. Now let's look at this. We'll spend a short time on this. This is not atypical of what's out there, particularly when it's in-house tests. If we look at this here, you can see, well, it's set up as I recommend with the bore site there. Bore site, the field probe is at the bore site. But if we look at what we're looking here, I think you can see on the left-hand wall, behind the antenna there, it's all set up for up to 1 gigahertz testing. That's all the ferrite tiles. And this is what this chamber was. Initially, it was for up to 1 gigahertz testing. Then, of course, along came above 1 gigahertz testing. And you can see the guides themselves mounted that absorber. And how old would you say this test setup was? And as I said, even since they put on the high frequency capability with these absorbers there, you can see there's a fair amount of wear and tear there, where people have, as they're putting tables in, and they've been rubbing up against the absorber and taking off the tip, worn out the tips. But this is not atypical, particularly of in-house testing, what's out there. The antenna, from this angle, looks pretty good, but it too was pretty much frayed around the ears and was quite old. But this is not atypical, and you, if you were in charge of this test lab, should feel free not to treat it as a holy relic. Don't be afraid of it, and have the courage of your convictions and do your own repairs as you require. So what need to speed up a little here. What are the likely faults? Well, the instrument could be damaged through over dissipation. A component could be damaged just through old age. And of course, it's often the case, the connectors and connections, and I gave you this story about the automotive story there, where the connector was so past its useful life that it just went into thermal runaway and destroyed itself. But I would recommend to you, and this comes from my background, I used to run a lot of projects, and not through choice, the customer would insist that you came up with a risk analysis. And I've put a very, very simple one here together for you. And this too will be on the website. It's not there yet, but it will be in a day or so. And it's a very, very simple way of coming up with mitigation steps once you've worked out what the chances are and what the impact is of any particular component or connector failing. So if we look at the top left hand there, oh no, if we look at the title, we're talking about something pretty old. What we were just looking at is 10 years plus. So failure there, we've got the cable might fail, connector might fail, amplifier might fail, antenna might fail, room might fail through rubbing up against it too much, coupler, PC, and software. And then we have risk and impact. Let's do impact first. You're the test manager. You've been given 4 weeks to get this product through a suite of tests. And the impact is, if one of these fails, what would be the impact on your program, on your test program? Is it disastrous, or you can get over it, and so forth? Then the risk applies. Well, what's the chances of this happening? I would argue, looking at that previous picture, that there's a very high chance of a cable failing, because all the cables were at least 15 years old, in my opinion. So I would say there was a chance. So basically, you've got a risk of what are the chances of this happening. If you've got all brand new cables throughout your test house, I would call that low risk. So the best way of teaching this is to show it yourself. You should actually do one. Let's look at the impact. Where I define the impact as the effect it will have on your suite of tests. Is it going to mess it up altogether, or is it a low impact and you'll be back online in a day or two? So let's look at the cable. Now I know for a fact that these cables were pretty old. I would put them at least 15 years old. So if we look at that, but the impact on the suite of tests, on the time you're given to get it, can you still get it done in the time, your allotted time? I'd say it was low. You buy another cable, yeah? It's not the end of the world in terms of affecting your project timeline. Connector, pretty much the same. We just had a look at that connector and how easy that was at the bulkhead connector I'm talking here to replace it. The amplifier, the impact on your test project, I'm going to say is high. The last thing you need is for an amplifier to go south. That's going to really affect your test program. Antenna, I would place at medium. The room itself, if that goes south, I would say that's going to really affect my test program. I'm going to call that high effect. You look at the coupler, how long before you identify a similar model online and get it ordered and so forth. I would say that a medium. It's probably going to hit you, I'm going to say a week or thereabouts. PC, I left that default for you to fill in. Why don't you have a go at this? You're going to have a PC running your EMC software, and I think we all know that a PC, the 5 years, they say it's getting close to the end of its useful life. And software, that again would be your own personal experience. What sort of software do you have? Is it prone to crashing? You know if it's prone to crashing. Are you using software you had years ago and you didn't get it updated to the latest version? There's a risk there too. And so there we are, low, low, high, medium, high, medium. And if we do exactly the same thing in terms of risk, if we look at that cable, they're all pretty old 15-year-old cables. I would say there was a high risk of a cable failing because of the age. It's old, 10 years and above. Connector, still same thing. I'm going to say is a high risk. Amplifier, I'd say medium. And the reason I say medium is with amplifiers, you get something called infant deaths, where it's going to fail within a year. But once they're going, they're going to last you a good while. But now they do degrade in performance. Don't let anyone tell you otherwise. Amplifiers age. The devices inside them age as solid-state amplifiers. So I'd say there's a medium risk of that happening, mainly through age. It's probably getting close to the end of its useful life, but I won't put it as high. Antenna, what's the risk of it happening? I think it's a fairly low risk. Antennas, if you look after them, if you're careful with them, it's a low risk of it conking out on you, unless it's really old as that one was there, in which case you might want to change that to medium. Well, I should have told you that when you fill these in, you have three categories. You have low, medium, and high. So if we look at the coupler, what is the risk of this old coupler going south? And I'd say it was pretty much medium. It's been used a lot. And again, I left that to you as an exercise, should you wish to do it. The PC, what's the risk of this PC conking out on you just when you don't need it to? And what's the risk of the software? Well, you've used the software so often you'll know that every now and again it crashes and it causes you problems. Now the idea is if you were a project manager and you were being forced to fill one of these risk analyses in, you would deal with the high first, rather for obvious reasons. There's a high risk of it happening and the impact on your suite of tests is high. So you deal with the HHs first and then work your way down. But here's the important thing with risk analysis, and this is why the customer wants you to do it. Should this happen, what are you going to have? What are your steps going to be? So for this high-low first row here, the cable, mitigation would be have spare cables, and failing that, guys, and I know it doesn't take long to order these, at least have the correct part number and lead time on file. So you're not doing this, you're not in crisis mode saying, oh boy, that's failed, I better get myself another one. Have it on file, or better still, have representative spare cables. With the connector mitigation, replace the connector ahead of time. You know full well this thing's 10 years old. You've seen how easy it is to replace a connector. Why not do it? And I would recommend adopt connector savers. There's the mitigation steps, and that's what the customer wants you to see. And that's if you had a customer using your test house, you probably won't want to be in a hurry to say, okay, some of these things might go south fairly soon, but they would love the fact that you have on file mitigating steps should one of the components fail. The antenna, this is where we get back to HH Systems, one of their features, because all they do is build antennas, they can ship out an antenna to you the very next day delivery. Then you have the room. This is the only one we'll really actually go into the mitigating steps in detail. But there are several things you can do to improve the performance of an older room. Then the coupler. Have the part time and lead time on file, and look for companies that will expedite for you. They will ship this thing out real fast. And just have it on file so you're not panicking on the day it fails. PC are left down to you. What should you do about it? Well, maybe buy a new one, huh? And software, again, that's down to you as a company. Let's see what you want to do. The one we're going to look at here is the high, because that is the most problematic one there. So covering those mitigation steps for the HH there, we can look to improve repeatability, not necessarily accuracy, but improve repeatability. Oh, and one thing I should mention is when you saw that picture of the antenna there looking at the boresight field probe, this was an in-house test facility these guys used before sending it out for third-party testing, and they had quite small EUTs. So in fact, they were pretty much aiming for a small area. They didn't have to get the full calibration plane done at 1.75 by 1.75. So it suited their purposes pretty well. Okay, and so you should route the cable using supports in the horizontal plane. I'll show you a picture of that in a second. And rather than just going back a meter from the antenna, then dropping to the floor vertically, a mistake in my view, and then having the cable snake to the bulkhead, I would recommend, because you can get far tighter bend radiuses, use semi-rigid cable, which is pre-formed for your specific bend you're looking for. And watch out for horizontal polarization too. Up to now, all we've done is talk about vertical, but you do not want horizontally run cables that will couple with the antenna. Given that you won't have a bulkhead, and I don't know why test chamber manufacturers don't do this, have a bulkhead right behind where the test height is. Any vertical runs that you will have to have, run them very close to that wall, very close to the absorber. In fact, left to me, it would go in between the pyramids of the absorber. I would suggest you that old chamber we were looking at the picture of there, I'd install separate immunity emission paths, and I would adopt savers. This is the mitigation set, remember. And I'd also use pallet placement. I've talked about pallets before, and I've used them myself before. And and replace pivotal absorber blocks. If you remember that old tatty room we were looking at, there's no reason you can't replace one or two of those blocks, the more important ones, the ones on the hot wall there behind the equipment under test. And you should find that it improves the performance considerably. So here we are trying to get closer to the idea, where I would argue that you need a straight line going straight out to that bulkhead, or the ideal height for a test. The test chamber manufacturers know full well about beforehand. But strangely, they seem to put them there. They took them away in the back corner of the sidewall. So how are you going to maintain vertical feed with that? You're not. But here, less than ideal. Can you see there's a semi-rigid cable, it's a quarter-inch semi-rigid cable. Once you bend that into shape, it will keep its form. It's really, really good. And look how tight the radius, the bend radius is. If you were to use a regular, say that blue type cable there, that would have to be quite a considerable long time going through that 90-degree turn. I would recommend these preformed shapes here. It was too hard for me to draw, but you can imagine if you had to go to the bulkhead, which was in the back of the sidewall there, you could run one of these, then a cable, and then another one up close to the plate and in. And there it is, best I could draw it. There's this semi-rigid cable. It's readily available. Putting the connectors really aren't too hard, but you do need a good size soldering iron. And there's your preformed, very repeatable. I mean, you mark these things up and you say, for this test, use this, and you take a picture of how the guy who's doing the test setup has to run that cable. Very repeatable and tight cable bends. Erasing a little bit here, we've got an arsenal of tests supporting test procedure. We could do a return loss. We would need high power attenuation termination for that. We could do a through loss. Or one thing here, erasing a little bit here, microphonic check. I used to do this quite a lot as a younger engineer. You would get a small wrench or a toffee hammer, and where you had suspect connections, say as it goes through the bulkhead, you would very gently look at your receiver or your spectrum analyzer and give it a little tap. It's known as a microphonic check. It's actually a tap test. You just tap it and see what happens on that screen, and it gives you telltale indicators as to whether that connector is giving issues. I would also say at the bottom there, reduce the floor effects using pallets. I've got a picture of a pallet coming up here, because I talked about them in the interference technology article I wrote on improving test chamber designs, mainly by using stealth processes. But reduce the floor effect, and we're going to show you that in a minute. Optimal cable room routing, we covered there using those tight radius bends. Improve the hot wall performance by selective replacement of older absorber. And here's the floor pallets. I wrote an article applying stealth technology, and there I drew a picture, side-on view of the ferrite tiling. Basically, it's not very well drawn there, but it's plywood, and screwed onto the plywood the ferrite squares, and then placed on top of them are the absorber pyramidal absorber, as you can see there. And these things were 1 meter by 1 meter, and you wheeled them in the place I was working at the time. And they run between the device under test and the base of the antenna, and they improve the performance of the room considerably. It's a lot easier to get your calibrated plane with those in place. Now myself, if I had my own test lab, I'd make my own. That is, rather than a meter by a meter, I'd chop that into 4. I wouldn't have the casters there at all, the little rollers there at all. I would just have these things so that you can easily pick them up because they're not heavy. Same makeup there, so you'd have the plywood and then the ferrite tiles, and then but nothing else at this point, and you'd lay them down all the way along in the manageable size, digestible chunks that you've made them into, and then I just place the 4x4 absorber on top and let gravity do the work of holding them down there. In summary, guys, if you've got a suite of tests to do, avoid fault finding in crisis mode when your test equipment lets you down. I recommend you do a risk analysis as a starting point. It's just good test management sense, and so you've got mitigation steps already in hand for this very important test that you're doing. I would have efficient fault location and prearranged corrections. The prearranged corrections come from the risk analysis, and the efficient fault location is having data on file of what you should expect at certain points in your test setup. Have test procedures in place. The quality guy will love you for that. And have the test data on file, as I just said there, and tie in with data trend analysis. That's good test management. Use the tap test, the microphonic test, for those hard to find intermittents. Give them a little tap. There's a sample test procedure on the AH test. It will be on the AH website, and that will be joined with others. And just a rider here. These are suggestions only. Assuming your chamber is out of warranty, and I certainly don't want you, when you have a go at some of these things, to go blowing up an expensive receiver or spectrum analyzer. So I do go into detail how to avoid doing that later on, but anything you do here, guys, you decide to act upon, it's down to you. It's not down to me or to AH Systems. It's up to you, and if there's any consequence of damage, that's all down to you. These are suggestions only. We're kind of run out of time there, but I do cover this on the AH website. And basically what you do is you start with your no damage input level on your receiver or spectrum analyzer there, and you work your way back through the gain of the preamplifier and establish what power level you need to go to place into the preamplifier for the test you're doing, and then you put in attenuators as required to ensure the no damage input is not exceeded. And then I do the same thing, no damage input, for a higher power test when you're using the big beefy amplifier. How do you avoid damage to your spectrum analyzer? And I go through that too. And there we go, guys. Thanks for attending.